Welcome to the Volvo240 Modernization Capstone project, updating the Volvo240 electrical system using a controller area network. Our technical directors are Mike Smith and Brendan Smerbeck. Our team consists of 3 electrical engineers and 1 computer engineer. Cameron Major, he's an electrical engineer. Myself, Jamie Hollins, I'm a computer engineer. Spencer Kubicki, he's an electrical engineer. And Timothy King II, he's also an electrical engineer. We're a student-led project. We've been given the unique opportunity to create and lead a capstone project. As a team, we have defined what this project will be. We had no prior experience with controller area networks or designing vehicle electrical systems. Replacement electrical components for Volvo240s are incredibly scarce and difficult to source, resulting to installing used parts removed from other 200 series vehicles. We want to remedy this situation and provide the Volvo community with a modern and reliable replacement. Anticipated best outcome. The anticipated best outcome, or ABO, is to produce a functional prototype controller area network or CAN bus for a Volvo240. The prototype should be able to process all required switches and signals that exist on an original Volvo240 electrical system. It should also include fault identification and increased vehicle data resolution. The vehicle systems will be split across multiple computers that communicate using the CAN protocol. The vehicle data will be visible from a digital display that will replace the current analog instrument cluster. Finally, test it in the vehicle. Here is a high-level overview of our overall design. So we did achieve our ABO. On the left, you'll see what we started with, which is nothing. And on the right, you can see our completed and built circuit boards. Team technical accomplishments. We have accomplished a lot during the lifespan of our capstone project. Notably, we have developed test circuits that imitate all vehicle systems, designed circuits to interpret many different vehicle signals, sent and received vehicle data on a CAN bus, designed and built printed circuit boards, and finally created a functional prototype. Economic impact. We are a group of dedicated students. However, we could become a team of dedicated co-workers. We may not have a massive impact on the economy. However, as a team, we could sponsor future URI engineers to help us improve upon our original design. Technical accomplishments. I was responsible for designing and implementing all aspects of the controller area network. I started by organizing all the vehicle signals from most to least important. This is because when a node tries to put a message on the CAN bus, it compares its current message to any incoming messages. If an incoming message has a higher priority than the message being sent, the node trying to send will first handle the more important data before sending its message. This process is called arbitration. In the version of CAN that we are using, arbitration is based off an 11-bit ID field. CAN considers all lows or zeros to be the dominant bits, and this is how a message's priority is set. An 11-bit ID field allows for a possible 2048 unique IDs. So an ID of 0 with a binary representation of 11 zeros will have priority over any other messages on the bus. Our present setup consists of 3 Teensies and a Raspberry Pi, all communicating over CAN. Using the Teensies enabled us to take advantage of their 10-bit ADCs. A CAN data frame consists of a data length code, or DLC, and a data field. The data field is a buffer of bytes that has as many indexes as described in the DLC. The 10-bit ADCs allowed us to send all vehicle data with just 2 bytes, while still giving us enough resolution for accurate data. The CAN programming was done using Python on the Raspberry Pi, and then the available libraries for the Teensies and the Arduinos. However, once the boards were complete, we migrated to using just the Teensies and the available FlexCAN T4 library and a Raspberry Pi. Subsequently, the Raspberry Pi code was rewritten in C++ with a couple of C libraries, socket.h, available on Linux, PyGPIO, a C library focused on efficient GPIO event handling, and finally SDL, a graphics library. As our project was born from a side project of mine, I am most familiar with the Volvo240. I went through every circuit in the vehicle to make sure that we could interface with it appropriately. Many of the switches in the vehicle in their original state closed circuits and supplied battery voltage to their associated components. This was an issue for us because we planned on triggering events in the vehicle from the Raspberry Pi's GPIO. However, there is a total max current and voltage allowed on each pin and all of the pins combined. To solve this issue, I decided to reroute most switches to ground, then pull the associated Raspberry Pi pins high with an internal pull-up resistor. On switch activation, the pin will be pulled low and we can trigger an associated event. This allows us to limit the current in and out of the Pi based on a regulated voltage source coming into the node. I also designed and implemented the digital display. I originally thought that using a graphical user interface library would be the best choice. However, in practice, this was not required. So I decided to utilize Simple Media Direct Library, or SDL. It is a wrapper around OpenGL that focuses on 2D design. The benefits of using SDL is that all textures and possible rotations can be rendered on startup. This drastically reduces the amount of processing needed during operation. Most of the display is static, with the exception of the tachometer and speedometer needle. They operate on their own thread so that they can move independently of each other and the rest of the display. This is important because the CAN bus sends the data required for each of these components from different nodes at a rate of 5 Hz. Being able to update the data and rotate accordingly is important. I also helped with the PCB design by optimizing each node and removing redundant components. I spent a lot of time drawing these circuits, ensuring that they interface correctly with my previously redesigned vehicle circuits. Here is the digital display and its individual components. Each image has its own surface that gets redrawn whenever a related event is triggered. Keeping these areas small is important. For example, updating the position of the tachometer needle 5 times a second would be computationally expensive if the whole dashboard had to be redrawn every update. Instead, updating the small portion designated to it is a much more elegant solution. The image on the right is captured from the startup animation, where every component is cycled to ensure that it has been loaded correctly. Here are some of the rough drawings I used to determine how the vehicle switches would interface with our designs. The image on the left is the direction indicators and hazard warning light circuit from the original Volvo240 technical manual. The image on the right is how it would interface with our prototype. A lot of the original components have been removed from the equation and subsequently simplifying the layout. This is the resultant dashboard node after working with the PCB design team to remove all unnecessary components. This was used as a guide for the PCB design team and was not intended to dictate the final layout. I would like to introduce our next team member, Cam Major.
Thank you, Jamie. My name is Cam Major and I'm one of the 3 ELEs on this project, along with Spencer and Tim. By the time we got into the realm of moving towards our PCBs, the majority of our designs were finalized and ready to go. Before then, we spent a lot of time testing out specific aspects of the car to see how everything worked and how we could implement our own circuitry to operate the components in the car. All 4 group members worked together to deconstruct the dash, sensors, and other elements driven by user input. Once all of the signals were fully understood, we moved into splitting up hardware design responsibilities between the ELEs. I was responsible for designing and implementing the circuitry that would operate the exterior lights in the car. Our cumulative design contains 3 nodes, with 1 at the dash and 1 in each of the front and rear of the car. My lighting circuits went on each of the latter 2. The design of each was virtually identical, just called at different times by the TNC on the node depending on which light was turned on or off by the driver. Each light, with the exception of signals like the headlights, which were shorted together as they turn on at the same time, has its own relay driven by an H-bridge. The decision to use an H-bridge to drive was made due to the original design limitations, as we were using an Arduino as the microcontroller. The Arduino was unable to keep a pin supplying voltage and continue to perform each of the other tasks required of it, so we opted to use latching relays. This would only require a pin to be held high for 30 milliseconds. However, to operate the latching relays, you need to be able to send current in both directions across the relay coil. Once we decided to go with a teensy microcontroller on each node, as opposed to the Arduino, we were able to remove the aforementioned restriction on pin usage and could hold pins high or low as needed. This resulted in my changing of the design to use standard relays in order to save money and allow for freer use of the H-bridge connections. With this design, although not implemented in our final product due to time constraints on the design phase, we are able to run 2 relays off of each H-bridge, which once done would reduce the footprint on the board and the total cost of the design. A few key considerations were given towards protecting the H-bridges. We destroyed more than a few chips before realizing that we had not taken into account the protections needed for the chip. First and foremost, we had nothing to protect the H-bridge IC from the flyback current coming off of the relay. We originally designed our own protection circuit, placed in between the output of the IC and the latching relay coil, which consisted of 4 diodes per signal. Since the current traveled bidirectionally, we needed a pretty bulky protection system. After we moved to the TNC and the non-latching relay setup, we were able to scrap the bulky design that we were using and purchase relays with built-in diode protection. These are the relays that went on our final design. Finally, we realized that the H-bridge needed to be powered up with a standby signal low, otherwise there was damage done to the chip. This didn't require a hardware design change, but it did require attention and slight modifications to the code written by Jamie. And as for general technical accomplishments and lab work, I helped in the design and implementation of the fuel and coolant temperature gauge operating circuits, and I assisted in basic lab activities such as circuit implementation, testing, troubleshooting, soldering, and helping with brainstorming and general circuit design. Here you can see a high-level overview of the exterior light operation. When the driver operates a light switch at the dash node sends a signal across the CAN network to the front node, for example, or the rear, depending on which light was turned on. That node receives a signal, and the TNC outputs a certain pin setup, either high or low, to drive the H-bridge IC, and the output of the H-bridge IC turns the relay on or off depending on what was requested, and that current sent to the exterior light to turn it on or off. Here you can see a small diagram, just a block diagram of the setup of the lighting circuit on each node. There's the CAN receiver and the TNC, which then output signals to the H-bridges. We use dual H-bridge IC, so there are 3 of them on each board. And the outputs of those are forwarded to a relay bank containing 5 relays on each board. And that relay bank would output the signal to the exterior lights, which are located off the node, wherever they may be in the car. On this slide, you can see the full layout of the schematic that operates the 5 relays as shown in the very middle of the schematic, driven by the H-bridges on the left. These signals are output to the lights and across our current sensing technology to detect bulb failures. This schematic was drawn by Spencer, and it is what was implemented in the final PCB build that we used. And on the right is just an example of general lab work. That was a chip that I had soldered together. And finally, here are a couple more examples of lab work. On the left, we have our model circuit for the blinker operation. This was used for testing and was essential for our design of the circuit once we were able to understand how they operated in the car. And on the right, we have one of our gauges wired up to a breadboard where we were taking measurements, understanding how the gauge operated and what drove it. And this was essential to the design of the fuel and coolant temperature gauges. And next, I'd like to welcome our next ELE, Spencer Kubicki, to talk about his technical accomplishments.
Thanks, Cam. Hello, I'm Spencer Kubicki. Over the course of this year, I've been involved in multiple very different facets of the project. I started the project lab testing components for their legacy cluster, such as the cluster's functionality as a whole, the speedometer, and more specifically, the fuel and coolant temp gauges. Additionally, I worked on creating a working concept for a bulb failure circuit to detect outages in the vehicle's lights. Then, during the spring semester, I focused solely on the creation of the printed circuit boards, as the rest of the team finalized the overall design of the nodes that I would then create. This process involved anywhere from schematic design to component placement to even designing 3D models for components themselves based on the real-life measurements. All throughout this time, I have done various other tasks, such as soldering test circuits and finding components online and drafting parts lists for them. Depicted here are some of the circuits I created myself, including the simple gauge testing circuit on the left, designed to test both at the same time, and on the right is the bulb failure circuit prototype, which, while it was not used in the final design, was a big leap forward in the team's understanding of I2C and its functionality over nodes. These are some examples of the complex circuits that Cam designed and I soldered, the directional indicators and headlights respectively. These are the schematics I drafted for the dash nodes PCB. The top left is the Raspberry Pi header and its connections, the bottom left is the Teensy 4.0, and the right is the 3 connectors leading to the other nodes. I also worked on the front and rear nodes individually before the design was finalized, where Tim took over for me, and combined the 2 into one schematic that could be interchangeable. These schematics were an ongoing process the whole spring semester, changing with each new component and each new design modification. The schematic had to be finalized in order to begin with a board design, otherwise there would have been far too many layout changes that would have needed to be made during production. This was the initial design of the dash node, with the Teensy to the far left and the Pi on the top side of the board. While this left a lot of room to fit components and routes, it also meant there was a lot of empty space that could have been taken off, so after trying some redesigns, I ended up changing the design to the following. This design places the Pi on the far left of the board, designing the board parameters around the Pis. This ended up taking off almost half of the original board space. The open space in the center is for the Teensy can header, but even then it's possible that the design could have been made even more condensed. In the interest of time, we decided to settle on this design for the board, leaving ideas like that to future revisions instead. This is what the final design looks like in 3D, and is quite similar to how it looks like in real life, shown in the next slide. This is the final product for the dash node, with some slight alterations due to design issues. It was deemed too difficult and too risky to reinstall the Pi's headers to allow it to fit on top of the board, so instead it was decided that the can hat would be placed on top of the board with the Pi underneath, sandwiching the PCB between them. With that, I would like to hand it off to my fellow teammate, Timothy King.
Thank you, Spencer. My individual technical accomplishments are divided up into 3 stages of the project. In the first stage, I helped figure out how the legacy cluster works and what information it displays about the car. I also helped design and assemble test bench circuits that simulate the cluster being connected to the car. The second stage was designing our proprietary cluster. I helped select hardware and design circuits as needed to read and process analog data from the car. I tested these prototype circuits and ensured that they met our design specifications. In the final stage of my participation, I focused on the printed circuit board design. I selected available components for surface mount solutions, and I designed the schematics and layouts for the printed circuit boards. This is the original instrument cluster for the Volvo240, and this was the starting point of our project. I helped answer the questions, what does this cluster do, and how does it do it? On the left is the tachometer, which is a simple square wave. In the center is the speedometer and odometer, which is a sine wave. On the right is the coolant temperature and fuel level gauges. These are analog voltages. On the bottom are lights such as check engine light and ABS light. These are highs and lows. After figuring out what the instrument cluster did, the next step was to build a test bench that simulates it being connected to the car so we could confirm its operation. On the left is a circuit I built with a 555 timer and 2 potentiometers that creates a square wave of variable frequency. This circuit replicates the signal seen at the ignition coil and was used to actuate the tachometer. After confirming the operation of the tachometer and what the ignition coil signal looked like, I began to design a solution to process the engine speed data. The solution was a frequency to voltage conversion circuit that produced a voltage proportional to frequency. This voltage could be more easily sampled and processed by our microcontroller. This solution was implemented similarly for the speedometer and tachometer, but with unique chips and supplementing components. Once working prototype circuits were established to accomplish each design requirement of the instrument cluster, I helped integrate the prototypes into a concise and cost-efficient design with minimal components. This step was required upon our decision to extend our ABO from working protoboards to working PCBs. This process rendered the front and rear nodes as very similar in operation and hardware, and played a big factor in our ability to produce PCBs. With our plans for hardware finalized around the availability of components, the PCB schematics were also able to be finalized by Spencer and myself. Spencer had already spent a great amount of time designing models for the components we selected and creating a starting point for each of the nodes' printed circuit boards. At this point, board design could be accelerated, and I took over primary responsibility for designing the front and rear nodes. Pictured here is a 3D render of a single board that satisfies the requirements for both nodes. The very similar hardware and operation of the front and rear nodes justified combining the design into one single design. This single board can be assembled as either the front or the rear node based on the hardware that it is assembled with. Subtle changes in the design were made so that the only difference in hardware between the boards would be the frequency to voltage circuit that is placed on it, as different hardware is required for the tachometer in the front or the speedometer in the rear. The other differences between the nodes is accounted for in software. In summary, we were successful in designing and implementing a controller area network for a Volvo240 and updating the electrical system. We aimed to have proto boards designed and connected to a test bench. We finished with the printed circuit boards and the ability to operate all systems in the vehicle. We have developed immensely as engineers, improved as problem solvers, and grown as team members. We would like to acknowledge Jack Murphy for keeping us organized and, more importantly, keeping us fed. Brendan Smurbeck for software consulting and hardware to software interfacing. Mike Smith for circuit design, PCB design, overall project scope and team guidance, and Dr. Sunak. Thank you for giving us this opportunity as a team. You put a lot of trust in us and that we could complete this task. It has been a tremendous challenge that we as a team and individually desired. The feeling of accomplishment and the intellectual rewards that you have facilitated are immense.